All right, so this is the third video in the atomic theory set. So we've previously talked about Dalton and his contributions to atomic theory. Then we talked about Thomson, who's credited with the discovery of the electron using the cathode ray. And now we are on our third kind of famous scientist in the discussion of atomic theory. And that person is Ernest Rutherford. So, coming pretty quickly after Thomson discovers the electron, and remember that while Thomson discovered the electron, he knew that there had to be some positive particles, right? Because recall that he knew atoms were neutral. They had no charge overall, and so he knew that if there were negative charges, there also had to be positive charges, but yet he was unable to locate them. So Rutherford was actually a student of Thomson's at the university level, okay, not so much like high school, but at so Thomson was a researcher, okay, and Rutherford worked for him. So Rutherford kind of picked up the ball, so to speak, and decided to carry on with Thomson's goal of discovering those positive particles that he knew had to be there, but he just couldn't find them. So he continued work on finding those positive particles. Okay. And he used something very famous. He used something that's referred to as the gold foil experiment. Okay, now I'm going to try to draw this for you, and bear with me because it's a little bit of an interesting setup. So, also when we're in class, we'll watch a video on this so that hopefully you can kind of have a bit more understanding of what was going on. Okay, so I'll give you a minute to try to draw that on your paper. So basically, Rutherford designed an experiment that had a piece of gold foil in the center, just like we think of aluminum foil, okay, but it was gold foil. And he had a box that contained positive particles. They're actually called alpha particles, and where they come from is not extremely important to this discussion. So he was able to, through some means, generate these positive particles, okay, and they were contained in this box. And then around the gold foil was kind of a detector strip. So if you think of, if you have ever seen a film strip, okay, like where film used to go in cameras way before the digital age, kind of like that, okay, kind of like a detector. And so what Rutherford kind of drew on his knowledge of working with Thomson. And remember, Thomson knew that the atom was filled with electrons, right? But that's kind of all he knew. So in Thomson and Rutherford's minds, the atom was mostly empty space because, think about it, it only had these few electrons floating around. Okay, so that's a big idea in this section. I'm going to get rid of that little drawing here, and I'm going to write that. So, so the atom was believed to be mostly empty space. And that's important. Okay, that's important for this discussion. So what Rutherford did was he took these positive particles, and I'm going to change my color, and he fired them at the gold foil. Okay, so he was able to send them out of this box and into the gold foil. Now, drawing on the fact that he knew the atom was mostly empty space, he assumed that the particles would go straight through the gold foil and hit on this detector strip directly behind the gold foil, okay? So that's what he thought was going to happen. And I like to explain this by, if you have a big tree in your backyard and it's winter and all the leaves are off the tree is probably said, like the top of the tree is probably said to be mostly empty space. So there's a really good chance that if you took a golf ball and threw it, through kind of the top of the tree, if all the leaves are off, there's a really good chance that the golf ball will go directly through to the other side. So it's kind of the same idea. So Rutherford started his experiment and he fired these particles at the gold foil, and that's exactly what happened. They went straight through to the back of the detector. However, all of a sudden, out of nowhere, he got one that did this. And then a whole bunch went straight through. And then you got another one that did this. So if you think about my tree example, which is easier to process, what's the only way, if you threw a golf ball into the top of a tree, that it could turn around and come back at you? Well, the only way is if it hit something, right? It can't just turn around in midair. So that's the conclusion that Rutherford was able to come to. So let's summarize this before we keep chatting. So he believed the atom to be mostly empty space. He thought those positive particles would pass straight through the foil. And, in fact, most did. But what he wasn't exactly prepared for were that a few bounced back. And what he was able to conclude was that they had to have hit something. Okay. And keeping in mind our rules for charges that like each other and charges that don't like each other, if these positive particles up here were ricocheting away from something, that means that they must have been of similar charge, right? If it was a negative charge that they were hitting, they would have stuck together. So from this, Rutherford is able to conclude a couple things. First, he concludes that those positive particles were hitting other positive particles. And two, he was able to conclude that because that ricocheting or that bouncing back happened only a very small percentage of the time, he was able to conclude that those positive particles were only contained in a very small area. And of course, we know that he's going to name those positive particles protons. And I'm assuming that you might also know that that very small area of the atom is the nucleus. So, what would Rutherford's model look like? Well, so Rutherford says in the center of the atom, taking up a very small amount of space, is the nucleus. And the nucleus contains all the positive protons. And floating out around the nucleus are the electrons. So that was Rutherford's model. I like talking here about how small the nucleus is because my picture doesn't exactly do it justice, but there's a statistic that goes something like this. If the size of the atom were the football stadium, then the nucleus would be a marble on the 50-yard line. So if you think about how big the football stadium is in comparison to how big a marble is, that's how small the nucleus is in the atom. So if we go back to this idea of the atom was believed to be mostly empty space, right? Is it mostly empty space? It is. Okay, so that's a true statement. It's absolutely a true statement, and that the nucleus occupies a very small volume. Okay, so very last thing, I think most of us know there's something missing from this picture, so we're just going to tack this on. It was like about 20 years later in 1932 that a scientist by the name of James Chadwick, discovers the neutron. And we learn a couple things about the neutron. It has no charge, and it lives in the nucleus. And its mass is approximately equal to a proton's mass, which means that the electron is much less massive than the proton and the neutron. We'll talk about that in our next chapter. So we don't do a whole lot of discussion on the discovery of the neutron. It's not quite as famous in terms of the experiment, but the person who discovered it, his name was James Chadwick. He discovers that the neutron is neutral, it has no charge, and it lives in the nucleus. And it's approximately, has the same mass as a proton, with the electron being very teeny in comparison. So we know today that the model of the atom looks something like this. In that nucleus are protons and neutrons, which I labeled protons as a positive. Oop, can't spell. And neutrons I labeled as an N. And then the electrons are out here. And this is the model that we accept to be true today. And this is pretty much where our discussion of atomic theory ends, because